So, today we're going to be covering the binomial expansion formula. So this is the formula we would want to derive. Probably have seen it before, probably recognize it once I write it down. So 1 plus x power n is equals to 1 plus nx plus n into n minus 1 over 2 factorial x squared plus n minus 1 n into n minus 1 into n minus 2 over 3 factorial x cubed, and it goes on. Normally for powers of like 1 or 2 or 3, these are probably the terms you will only care about, because when you have a term where it's power 4 over here, something like that, when you're dealing with a power 3, you're gonna have 3 minus 3, which will give you 0. So these are the only terms for 3 and below. More terms, you continue the pattern. It's going to be, for example, for n is equals to 4, you will go n into n minus 1 into n minus 2 into n minus 3 over 4 factorial. And that's basically how the pattern goes. But the problem is, we're given this in class and we are never told how or the proof for the equation. And that's what I want to cover in this lesson today. So, before we get into that, we have to know a little something about Taylor series. Taylor series. Basically, all that Taylor series are is trying to make a polynomial look like some other function. That's all it is, right? So basically, what defines a graph? We have to look at what defines a graph to be able to make a polynomial that will match that graph. So what defines a graph exactly? So a graph is basically defined by one, its starting points, how high or low it is in the y-axis. 2, its rate of change. 3, its rate of change, and its rate of change, and its rate of how many rates of changes I've mentioned before, plus 1. That's what defines a graph. Anything that matches the rate of change and the rate of change and the rate of change, that's what's going to give you the same graph as your function. So for example, let's start with a graph like sine x. Let's say y is equals to sine x. And we're trying to find a polynomial that will match this function, y is equals to sine x. And because sine x, okay, for example, I've said that the starting point matches is what determines the graph. That's the first thing that determines the graph. The starting point can be determined by this equation alone. The rate of change has to be determined by the derivative. So you take the derivative of this, you have dy over dx is equals to cos x. By the way, there's going to be another video on the explanation of this, y sine x, when it's the differentiation of sine x is cos x. I'll explain that in a later video. Right now it might be a bit too long, and I don't want the video being over 20 minutes. Hopefully it's less than 20 minutes, we'll see. But anyway, let's continue. The rate of change, d squared y over dx is equals to differentiation of cos is negative sine x. We can keep going. d3y over dx 3 is equals to differentiation of sine is negative cos. Now differentiation of negative sine. Differentiation of sine is cos, rather. Now differentiation of negative sine is negative cos. Sorry, I went ahead of myself in that one. So cos x, negative cos x. It's easier just to leave the brackets, I think. I mean, it doesn't cause much of confusion, so good. And the x's now look too far away. x, 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 x. Okay. Differentiation of negative cos. Thing is, for the differentiation of negative cos, the differentiation of cos alone is negative sine, so the differentiation of negative cos should be negative sine, which is just positive sine. So it loops back up here, it loops back and the pattern is generally, it just generally continues like this, because once you go back up here, you're going to go back down there, and then back up. So you can see that you can never really get to like a point where the rate of change will be 0. It's always going to be something. For polynomials, on the other hand, you're going to get to a point where the rate of how many whatever's rates I've said is going to be 0, right? For example, if you have a plus bx plus cx squared, you'd have that alone. You're going to end up with the first derivative, easy, will be a goes away, b stays, c, the 2 drops down, and you're left with 2cx. So it's going to be b plus 2cx. The derivative of that would be b going away, 2c being left, and the x going away, so 2c. Derivative of that will be 0. So the problem is with polynomials, it's always going to get to a point, at least for finite sums, it's going to get to a point where the differentiation will be 0. And that's kind of a problem. So the thing is, for you to get the perfect graph for y is equals to sine x in terms of a polynomial, you'll have to have an infinite sum. An infinite sum of x terms in increasing order to infinity, because if you don't have an infinite sum, the finite sum will get you to a point where the differentiation is just 0. Alright, so let's try to find at least like an approximation around the value 0 for y is equals to sine x. So the thing is, when we have an approximation, because the thing is, when we have higher order terms, for values next to 0, you're going to end up having a value that is really small. When you have x power 4, even x power 7, yeah? X power 7, when the value of x is really small, x power 7 will be 0.0000. Let's pick a really small number like this. 1 power 7. Thing is, this number is going to get even smaller. So you can approximate for values near 0 the graph y is equals to sine x. Yeah? So let's do 4 terms. 5 terms of the polynomial where that will approximate the graph y is equals to sine x. So the polynomial is a plus bx plus cx squared plus dx power 3 and ex power 4. Okay, so first derivative, just the function by itself, y is equal to sin x, should tell us at 0 what is the value of sine x. So the value of sine x at 0 we know is 0. So because let me put the constants in a different color. A plus B plus C plus D plus E. Those are the constants. Okay, so we know that sine of 0 should be equals to A, because when you plug in 0 into the polynomial over here, we have these terms over here going away. This is not even the first derivative, this is just the plain function by itself. We're trying to match the value of y at 0 to the value of the function at 0. So when these ones are not taken the first derivative of, when it's just the plain function, these x terms, they go away because we're working with 0 over here. So that means that a should be the only one left. Sine of 0 is 0. Sine of 0 should be a, right? Sine of 0 should be equals to a, and sine of 0 is 0. So a is 0. Okay. Next, we take the second derivative of both the functions, and we say those two must also match for you to get a good approximation. So sine of differentiation of sine, cos. So cos 0 should be equals, when you derive this equation, you're going to be left, a goes away, this x over here goes away, you're going to be left with b plus 2cx plus, and all the other terms on the right will have an x in them. Because we're working with 0, the x should go away. So you should just have b. So cos 0 should be equals to b, which is equals to 1. Cos 0 is equals to 1. Okay, so let's go to the third. Negative sine of x, negative sine of x, negative sine of 0. Now this is the third derivative. Taking the third derivative of this equation, again, a and b now go away, right? C, now the x over here goes away, and all the other terms on the right have a value of x. So those terms also go away when x is equals to 0. So negative sine of 0, negative sine of 0 should be equals to c, should be equals to, important point here, by the way, when we take the third derivative, the 2 hops down for the first one, and then the 1 that's left hops down again to leave 0, so x power 0, which is 1, and the x goes away, right? So it should be 2c. So it should be equals to 2c. 2c. And that negative sine of 0 is 0. And then the third derivative, rather. We were working with the second before. I think I may have confused third with fourth a bit, or second with third, one of the two. But this is the second derivative. This is the first. This was just a plain function by itself. Third derivative is negative cos x. So negative cos x, now we're taking it near 0. I mean, at 0, we're approximating it at 0. Negative cos x should be equals to the third derivative of this polynomial. And what's the third derivative of this polynomial? Anything with x power less than 3, where the power is less than 3, that goes away. 3 itself, the x will go away, the constant d will be left, and the value with e in it will become 0, right? Because we're using 0 as our x value, and anything times 0 is 0. Basic stuff. Anyway, so this will be equals to 3 hops down becomes 3 times dx squared, and then when you do it again, it's going to be 3 times 2 dx, and then for the x to go away, it's going to be 3 times 2 d and no x power 0, but then the x power 0 is a 1, so no x. So there's a pattern you might have realized here. It's going to be 3, and I'll point it out in a bit. It's going to be 3 times 2 times d, let me get the colors right, d, and cos 0 is 1, negative cos 0 is negative 1, which is the value of 3 times 2 times d. Now, let's go to the fourth one. The fourth one, we go back up, and now the fourth derivative is basically just sine. The fourth, it's itself, and it follows a nice cycle, which I find quite fascinating. It goes sine x, cos x, negative sine x, negative cos x, then sine x again, pattern repeats. You get the point, yeah. So sine x, sine 0, it should be equals to, now if we were to take the fourth derivative of this function, we've done the first, second, third, now fourth. Fourth derivative of this function, the polynomial I'm talking about, all values, all terms with x power something less than 4 will go away. And those are the d, c, b, a, those ones will go away. And the only thing left is e power 4x, which we need to derive because this is a fourth derivative. We do it 4 times. So 4 times e x power 3, then 3 times 4 ex squared, and then 3 times 4 times 2 ex, then 3 times 4 times 2 times 1 e. Hopefully I got that right. So let me write that down. So it's going to be 4 times 3 times 2, and then times 1. I don't really have to write that. It's just going to be the same as not writing it. E, and sine 0 is equals to 0. All right. So hopefully you notice the pattern. So you can see that on the terms over here, you see that it becomes 2 factorial over here, which I'll replace 2 factorial there. 2 factorial. This 3 times 2, it's going to become 3 factorial. Because we're just taking the power and multiplying it by n minus 1, n minus 1, n minus 1, n minus 1, where n is changing every time. You take the new value of n, minus it by 1, and then multiply it by the old ones. That's basically what a factorial is. So this one's going to become 4 factorial. 4 factorial e. Now, we have each of these. And now we can form our polynomial for an approximation of sine x near 0. So a is going to be equals to 0. 0. B is equals to 1. C is equals to 0 because anything times anything, when these two multiplied are equal to 0, then of course the C has to be equals to 0. C is equals to 0. D is equals to -1 times, divide by 3 factorial. So -1 over 3 factorial. And E is going to be, let me just keep these neat because I think it looks better. E is going to be equals to 0. Whoops. Yep, 0. Okay. Hopefully you've understood this concept. Now let's just form back our polynomial quickly. So remember a is 0, so it's going to be 0 plus bx, which is just, since b is 1, it's just going to be x. So it's going to be the polynomial, let me write this in green, x plus, and c 0, and then d is -1 over 3. -1 over 3. So I can actually just change this to a negative 3x minus 1 over 3 factorial x cubed, and then e is 0 again. E is 0, so the polynomial is just equal to this. This is not the best approximation because we're not matching everything. We're not matching the rate of change and so on. We're only matching up to like the 4th derivative. But the thing is, with infinite polynomials, now is when you get to match the thing completely. When you have this pattern, which by the way is going to end up being 0, 1, 0, negative, a negative value, then 0, and then a positive 1, then 0, then a negative value, going on. And of course the factorial over here just adds up. It's going to be 3 factorial, 4 factorial, 3 factorial, because you're skipping actually. Because you're skipping, you're going to skip the 2's, the 4's, the 6. You're going to skip all the even numbers of factorial. And this is only for sine. Cos, I think, does the opposite. It skips the positive values of the polynomial, skips the positive values, so it doesn't have any positive, so not positive, but any even numbers as the polynomial, in the polynomial. Hopefully you get the point of that. That's the polynomial for approximating sine of x near 0. I've realized that we've gone past time already, so there'll be a part 2 coming up in just a bit. So, and that'll basically cover the rest of what is needed to derive this equation.